Hi everybody. In the last video we talked about the size of a nucleus and the fact that there are isotopes of the different elements, and we label them with whatever the symbol is for the element. We have the atomic number and the total number of nucleons, which we call the atomic mass number. And we talked about the fact that for the larger nuclei, even though you're putting more neutrons in between protons, that once the atom gets so big, it's just inherently unstable. So what today we're going to talk about is radioactive decay. So this is when your nucleus is unstable and it's going to decay in something more stable. You probably know that there are three types of decay, or we designate three types of radioactive decay, and they're designated by the type of particle that comes out of the nucleus during the decay process. I should mention too that this radioactive decay is completely random. We don't know when a single particle is going to actually decay. There's no way to predict that, but you can predict the probability that so many are going to decay over time when you have a large sample. So the three types are alpha decay. So this is when you have an alpha particle, which is a helium nucleus, comes out. Then you have beta decay. We have beta minus and beta plus. So this is when an electron or a positron, the antiparticle to the electron, comes out. And then we also have gamma. So this is when a high energy X-ray comes out. Now, high energy X-rays are very hard to stop. They go right through your hand, they go through paper, they go through cardboard. You need quite a bit of thickness of lead to stop most of these gamma rays. Beta particles, electrons, can easily be stopped by your hand. Now they might go through a sheet of paper, but they cannot go through your hand, so your hand skin will stop them. Alpha particles can be stopped even by a thin piece of paper, or even a fairly thin sheet of mica. So gamma ray is hard to stop. Beta, electrons, positrons, a lot easier to stop. Alpha particles, very easy to stop. Okay. So during a decay process, there's a couple things. If you want to, let's look at the decay of U-238, the most common isotope of uranium. So it has 146 neutrons and 92 protons. So when it decays into, it alpha decays. So you get a helium nucleus that comes out. Now, for all decay processes, for all these radioactive decays, you have to conserve charge. And you conserve number of total nucleons, so number of protons and neutrons. And you conserve energy too, of course. So during this process, we had 238 total nucleons minus 4. So that gives you 232 nucleons. 234 nucleons. So whatever we have is going to have 234 nucleons. We had 92 positive charges, and now if you take off 2, that's going to be 90. And if you look that up, that's actually thorium. So U-238 is going to decay into helium plus thorium, Plus, since this happens naturally, it turns out there's going to be some energy released. So if you look at the energy, total binding energy of U-238, and then you look at the total binding energy of thorium plus helium is less binding energy total than U-238. So where does the rest of that energy go? It goes off into kinetic energy. Kinetic energy of mostly the helium atom in this case. And by the way, I said that wrong. The binding energy per nucleon goes down, gets higher. I'm sorry, gets higher for this than that. Yeah, the total binding energy that's wrapped up in this is not equal to, it's more than the total binding energy of these two. So you have excess energy released. And again, it goes into kinetic energy of the helium nucleus. So let's look at another decay example. Let's look at, this is actually carbon-14 is a pretty rare isotope of carbon. I think it's like 1 per trillion. So it beta decays. Now, the electron is not a nucleon. It's not a proton or a neutron. So the daughter, so we call, by the way, the initial unstable nucleus, we call that the parent. And then it decays into alpha, beta, gamma, and then the daughter, what we call the daughter nucleus. So the daughter nucleus in this case, since that's not a nucleon, it will have 14 total nucleons. But look, we had a negative charge, so charges conserve too. We had 6 positive charges, and here we have a negative charge. So we got to end up on this side to have still 6 positive charges. So that means this one must have, the daughter must have 7 positive. 7 minus 1 is 6. So that's, of course, nitrogen. So that will be the reaction here. And again, plus there'll be some energy released. So we went from 6 protons to 7 protons and an electron. So what happened? Well, in beta minus decay, a proton gets converted to a neutron. So let's just take a minute to talk about that. So the nuclear force, if you're going to talk about the force, you can talk about the potential. And we can talk about a potential for neutrons and protons. Or we can talk about the potential for neutron-neutron interactions, or proton-proton interactions, or neutron-proton. So as far as we know, the nuclear force, I mean, these things are bound together, so it's a negative energy. And the depth of the well goes down to, you know, roughly something like 42 MeVs. You can calculate that. That's sort of the most tightly bound interactions are on that order of energy. And then there's a certain radius. So let's make this the distance between neutron, or proton, and proton, or neutron and proton. Let's talk about the neutron. So at a certain radius, the nuclear force, which is very small, the nuclear force goes back up to 0. So what the shape is like this exactly, I don't know. When you have the proton-proton interaction, though, proton-protons are, you get this Coulomb repulsion. So the nuclear force holds them until they get far enough away that the Coulomb repulsion will take over. So for protons, the force might look something like this, where here's still 42 MeV. So then here, if it's this, say this is neutron, neutron, you might have neutrons at these different energy levels in here. Or here you have the protons. Okay? Now we're not going to get too into that, but let's talk about the beta decay where you have a neutron changing into a proton. How does that happen? So I'm going to show two potential wells here. R is this way and this way. This side is for neutrons. So here's our potential well, and then it's occupied by, let's look at the higher energy state. So here's neutrons. We got this neutron, and over here on this side I'll do the protons. This is not just proton, proton, but this is just our proton energies. So let's say on protons, we put a couple more neutrons here. On protons, maybe we have less protons. So what we might have is a energy level here that will allow us to have another proton. And we have a neutron over here that's at a higher energy. Well, the nucleus would like to be a little lower energy. So what could happen is this neutron changes into a proton and fills that energy level. So that's what's happening. So we can have neutrons changing into protons, and this was figured out by Enrico Fermi in the 1930s. He came up with a theory of beta decay. It's been changed a little since his time, but it's basically the same. Of course, we can also have the other way can happen. We can have a proton that might be at a slightly higher energy than a neutron, and there's an empty neutron shell, and the proton can change over. So you can get a proton change into a neutron too. Here's the interesting thing is a neutron can actually even change into a proton outside the nucleus. It's energetically favorable for that. But a proton can only change into a neutron inside a nucleus. That's not energetically possible outside the nucleus. Although there are people that look for this. And then gamma particles can come out for various reasons. One, maybe you have an alpha decay, and like our U-238, we said transforms into thorium. And then the helium. So you get the helium, but sometimes then what will happen is the nucleus will be excited after the change and will have not gone down to its ground state energy yet. So so then the nucleus is excited that's left, so maybe I'll excited nucleus of the daughter, and then as it settles down it will throw out a gamma ray. So you can get that, basically it looks like it comes out during the alpha decay process. Or sometimes you can just excite the nucleus, and when it de-excites, it throws out a gamma ray. But you usually get a gamma ray coming out when you have alpha decay too. Okay, so let's actually talk about the mathematics of radioactive decay. If you set it up, the number of particles that you're going to have at any one time, so as a function of time, depend on the number of particles you have, and the change in time, the number of particles you have, are going to depend on the number of particles you started with. Whenever you have this kind of relationship, it's going to be an exponential relationship. So even more generally, we can just say this, that the change in the number of particles you have depend on the number of particles that you have at any time. Okay? So if I rearrange things here, I get this, get the natural log of n. Now I'm not doing any constants here, so maybe I should do from n naught to n, from time 0 to time t. So then I get natural log of n over n naught equals t. Oh, I forgot an important thing. It goes down. The change is negative. So you got to put that negative sign there. So I'm going to move that negative sign over to here. There we go. So yeah, this just tells you that the change is negative. We're assuming the number of particles goes down as they decay. So then move the 1 over n over here, leave the negative sign over here, bring the dt up, integrate, and we get this. The inverse function of the natural log is the exponential. So if I take the exponential of a natural log of n over n naught, e negative t, then this just gives me n over n naught equals e negative t. So I get the number of particles is the number I started with. It looks something like this. Now, in general, there's a proportionality constant that we put in here. And so we'd say, first we would say the number of particles with respect to time is proportional to this, and then we would say put the proportionality constant in there. So if I did that, what we're going to have is n equals n naught e to the negative lambda t. And that proportionality constant that I just put in there is going to dictate how fast. So this is an exponential decay that we start out with n naught over time. And that exponential decay, that lambda tells us how fast that's going to drop off. So it's called the decay constant. Okay, so that's the number you have at any one time, and it changes as time exponentially. Now, if you have a lot of particles that are unstable, you'll get more decays per minute, for example, than if you have fewer particles. So you could also write the rate, so this is going to be rate of decay, so number of decays per second or minute per time. At any one time, the rate of decay is going to be equal to whatever the initial rate was when you started. Because we usually measure the rate of decay, we have Geiger tubes that tell us how many decay products are going into the Geiger tube at any one time. What a Geiger tube really is a tube, metal tube, where the case is grounded, and then you have a wire going inside, and this is maybe it compared to the ground, it might be 10,000 volts. then you have a very thin window here that will allow electrons, for example, to go through. If they go through, this is positively charged, they're negatively charged, they're going to go right to that wire, and then electronics are going to count that as a pulse. And so you can count how many electrons, for example, come in here. We also have a gas in here. So the electrons might hit the gas and knock off electrons, or a gamma ray could come in here and ionize, knock off electrons off the gas atoms, and those electrons will go to the wire. Same thing with an alpha particle. It can go in. So for an alpha particle, though, you have to make this window very thin. So a lot of detectors only detect electrons or gamma rays. So let's talk about the half-life. So when you have, let's say we have this carbon-14, and we know it's unstable. And like I said, you can't tell when a single atom is going to decay, but when you have a large sample of them, you can tell on average. So the amount of time when you expect half of those collection of atoms to have decayed is called the half-life. So in this case, we said this was going to be a beta negative decay. So how do you find the half-life? Well, the half-life is when, if you're counting with your Geiger counter, and you start counting with an initial rate. So we have this equation. So when when your number of counts per minute go to half of what you started with, it gives you this. That's when your time is considered to be your half-life time. So it takes that much time for your rates to go down by half. So if you look at this, we can cancel out both of those. We'll have 1/2 equals. Now if we take the natural log of both sides, the natural log of 1/2 is negative 0.693, and then you get, if I divide by negative lambda, I get. So if you know your half-life, you know that decay constant, or if you know the decay constant, you know your half-life. So another guide to figuring out how many of your particles have decayed is that when you have 1 half-life, you've lost half of your particles, right? When you have 2 half-lives, you've lost, you only have 1/4 left, so number of particles left. 3 half-lives, you have only 1/16 of them left, and so forth. So let's do a problem. Okay, this is problem 1175 from your book. So again, we have this, and we have T1/2 equals 0.693 over lambda. So let's say we have some counts where we got our Geiger counter going in front of an unknown sample, and we are initially counting 115 decays per minute. Okay. So let's say we let this go a long time, so this thing's going to probably have a kind of long half-life. Let's say we go 4 days and 5 hours. After 4 days and 5 hours, the rate is equal to 73.5 decays per minute. Okay, so then the question is, what is the half-life? So there would be a couple ways we can do this, but I'm going to go back up. The more accurate way is go back up to this, and if I divide by R naught, R by R naught, I get this. And if I know the time was 4 days and 5 hours, I can convert that to minutes. That's going to be, I've already done that, 6,060 minutes. So let's say I know that time. Take a natural log of R over R naught. That's going to be negative lambda times my time. So lambda is going to be natural log R over R naught minus divided by that time. It's not the half-life, because has it dropped in half? No, not really. Instead of a 0.5, it's probably like 0.66 or something. So let's put this in and get an answer. We put in 73.5 over 115. That'll give us a negative number. We'll cancel out that negative over 6,060 minutes. And I end up with lambda is not very big, 7.61 times 10 to the negative 5 inverse minutes. So now I can look at the half-life. The half-life is 0.693 divided by so my units will be in minutes. And I get 9,100 minutes. R, if you were to see, there's 60 minutes per hour. There's 24 hours in a day. So I want to convert this to days. So 60 minutes is 24. Oops. It's 24. So give me days on top. So that gives me, that'll be 6.3 days. I'm sorry, I was writing way down here. So it's going to take 6.3 days for this thing to decay Okay, what we haven't mentioned is when nuclei will undergo beta decay versus when they will undergo alpha decay. Let's just mention that, and then let's talk about carbon dating. So the general rule is beta decay occurs when the total number of nucleons is less than 200, and then otherwise they go alpha decay. So that's the general rule. But these daughter nuclei, when you undergo alpha decay, are big, and they can be themselves radioactive or unstable. When that happens, we know the decay sequence. There's only 4 types of sequences that occur. So the 4 types of sequences are called 4n, 4n plus 1, 4n plus 2, 4n plus 3. So basically, this sequence is if you can take your total number of nucleons and divide it by 4, then our 4n, you figure out what that is, our 4n, how about that, equals A. Then it will undergo alpha decay along this sequence. If you can take 4n plus 1, and n is some integer, equals A, then it will decay under this sequence. And for example, 232, or thorium. If you take thorium-232, if you take 4 times 58, that's 232. So it will decay under the 4n sequence. So you start with 232 thorium, and it alpha decays. And if you look in your book, they have these, I think they have the decay sequence for this. So they represent an alpha decay, so that goes down. You lose 4 nucleons, so this will be 228. And you lose 2 protons, so this turns into radium. And then if it goes this way, you get a beta decay. And then there's 2 beta decays. And for each beta decay, you get a neutron changing, beta minus decay, you get a neutron changing into a proton. So this goes back up to thorium, 228. And then you'll get an alpha decay, and so forth. And each of these parts of the sequence have different half-lives. But you can look up, and you can find out that what's eventually going to happen is this is eventually going to turn into lead in the end, either through a last alpha decay or last beta decay. So if you look in your book, I think it's figure 1118. This is the one I'm thinking about right now. So that's alpha decay. And actually what's happening in alpha decay, if you look at the potential well, the overall nuclear potential well, you have a helium atom in here somewhere. You have 2 neutrons and 2 protons rattling around in here. They can have an energy, they're above 0, and if they can tunnel through this barrier, that it comes out. And it goes back and forth, hits this about once every second. So every once in a while, then you'll get one tunnel through. Depends on the width of this barrier here. For bigger atoms, it's a little bigger, but these, well, I'll just leave it at that. So the last thing I really want to mention is carbon-14 and how we use that to carbon date things. So you can use a variety of unstable atoms that are in substances, in wood, in us, that you can use for dating. But we always talk about carbon dating, so let's mention what that is. So carbon-14 is made in our upper atmosphere through nuclear reactions. I think it's mostly particles hitting nitrogen and converts some into carbon. Now, as far as we know, this has been happening for a long time, and the most stable isotope of carbon is carbon-12. But the ratio of carbon-14 to carbon-12, because the rate at which carbon-14 is made in the upper atmosphere, we think has been constant for a long time. So we think this ratio has been constant for a long time. And that ratio is about 1.3 times 10 to the negative 12th. Very small. So when we breathe in, or when trees take in carbon, we are taking in some carbon-14 too. But carbon-14 is unstable. It's radioactive, and it has a half-life of 5,730 years. So once something stops taking in carbon, it dies. A tree or a human or whatever it is that's alive that takes in carbon, and when they die, that ratio starts getting even smaller because you start losing the carbon-14. So let's do an example. So let's say you get a piece of charcoal that came from some wood, and the charcoal, you have 25 grams of charcoal, which is basically carbon. And you find that the carbon-14 activity, let's say we get 250 decays a minute. I don't think that's too much. So how long has the tree been dead from which the charcoal came from? Okay. Well, first of all, the rate so it goes like this. We know what lambda is for this because we know the half-life. Lambda is 0.693 divided by 5,730 years. We don't know how much time has occurred. What we'd like to know is what the initial rate should have been. Well, here's a way we can do that. We can find out how many carbon-14 atoms there should be in there. Number of carbon atoms implies number of initial carbon-14 atoms. If we know the number of carbon-14 atoms that we had initially, which we'll call N naught, then the initial rate should have been the number you have times the number of decays per second, which is dictated by that lambda. Number of particles initially. Number of decays, in this case per year. So that should have been the initial. So we know this, we need to find that. And we can find it by knowing how many carbon atoms we have to start with. We know we have 25 grams of charcoal. So if we start out with, move this out of the way, 25 grams of charcoal, and carbon 12 would have 12 grams per mole. It's mostly carbon 12. So this will tell you the number of moles you have. And then 1 mole is 6.02 times 10 to the 23 nuclei. So this gives me 1.24 times 10 to the 24 nuclei, if I did this right. And the ratio of carbon-14 to carbon, we said, was 1.3 times 10 to the negative 12. So if I take that times the 1.24 times 10 to the 24 nuclei, this is going to be number of carbon-14. I get 1.6 times 10 to the 12 nuclei. So there should have been this much carbon-14 roughly at when the tree died. So the initial rate should have been 1.6 times 10 to the 12 nuclei times, what did we get for the decay constant? 0.693 divided by 5,730. That's going to be a pretty big number, so that's decay per years. And let's see, what do we have? Let's change it to minutes. Let's change lambda 0.693, 5,730 years, and let's see, 1 year is, we use this all the time, I should know, 3.16 times 10 to the 7 seconds. And what do I want? I gave us the decays per minute. So 60 seconds is a minute. So this will give us the number of decays per minute. And that's equal to, it appears, 2.3 times 10 to the negative 10 decays per minute. So R naught should have been our number we started with, which was 1.6 times 10 to the 12 nuclei times 2.3 times 10 to the negative 10. So I get 367 decays per minute. So that was our initial, and now we have R, which is 250. If I divide that by R naught, I get e to the negative lambda t. So natural log of R over R naught divided by negative lambda should be the time. So I'm going to get, and I want that time, let's put that time in years. Did I do lambda in years? So this is decays per minute. For a year, it would be 0.693 divided by 5,730. So natural log, natural log of 250 over 367 divided by negative 1.2 times 10 to the negative 4. This will be in years. So let's see. I get 3,200 years roughly. Just to two significant figures. So that's how carbon dating works. Again, when something dies, you know what the initial ratio of carbon-14 to carbon is, the 1.3 times 10 to the negative 12. If you know what the rate is now, or the number of molecules you have now, carbon-14 molecules, you can, if you know the half-life of carbon-14, which we do, you can get the decay constant. In this case, I did it in decays per minute because we had R in the rate in decays per minute. Then we found out using this again, that will tell you if you can estimate how many carbon-14 molecules you started with, you can do this to get the initial rate, and then you can stick it into this equation and get the time. So there's how carbon dating is work. In general, that's how it works. There's other atoms that they can use for carbon dating rather than just carbon-14, but again, it's the most the most famous, right? So, okay, so that's it for radioactivity right now. We could talk more, but that's a quick sort of